Welcome back to ECE 442-542. I have quite a few announcements and a fair length of goals, but you can see in black there's some supplemental material, and they've tried to be organized relative to where we've covered those topics. We're in Unit 5, and Homework 5 is due on Monday. One of the goals for today is actually to try to help you or give you hints on how to work Homework 5 problems to make it go even quicker. Hopefully, that's the plan. And if you're in 542, your deliverable number 1, which is essentially tell me what you're trying to do with your project, not a 20-page write-up. It needs to be no more than a page and probably less than that as far as explaining what you're trying to do with your project. That's deliverable number 1, and there should be a Dropbox for that. Relative to these supplemental videos, that's what the S stands for. Today's lecture is video 5 or lecture 5.4 to sort of organize this. A couple of lectures ago we were talking about performance criteria or design specifications, and there's a few lectures that supplement that as far as sampling, competing performance specifications, what happens when they all three don't meet or achieve each other simultaneously, can you adjust some of those performance specifications, and creating T sub C of S. That's the first homework problem and the second homework problem. And there's a supplemental video beyond what we will do today. Not yesterday's, but the lecture before this one, we talked a little bit about the Ragazzini design technique or control strategy, and I'm giving you more of a general overview of control design in this supplemental video. And after tonight's lecture, I'll try to make this one available, which is another example. And I like to just say you can learn about intersample ripple. We've talked about deadbeat controllers. Now what happens with intersample ripple, or what does that really mean? And now you can actually have some variation in your continuous time waveform between the sample points, and that's what I'm meaning by intersample ripple. And that's another design example using Ragazzini, and that concludes or sort of summarizes what you might want to keep in mind when you're designing controllers at the end of that. And that's why I like starting with the Ragazzini design. It gives you some perspective on what issues are important when you're designing controllers. You probably won't want to design with Ragazzini, but at least we start talking about not canceling unstable poles and zeros, a desired closed loop transfer function, how do we sample. Those kinds of concepts are important, and that's what Ragazzini actually helps focus our attention on. There's actually a write-up on the Ragazzini design approach, a few pages from a textbook, and that's available on D2L. The exam number 3 material should be available to you, and we will have a review session, not next Monday, but the week after that, on the 9th of April, and that's actually when homework number 6 will be due. And if you have a question or topics for that review session, there's a quiz on D2L that you can type in or provide a written piece of material that hopefully communicates to me what it is that you would like to have covered in that review session. Likewise, you should have access to the Shams Outline, that book, through the U of A library. That's one of the course resources, and chapters 13 and 14 might help you gain even more insight into unit number 6 material, which we're going to be doing a different controller design, which will be based on a root locus strategy. And if you've had a controls class before, maybe you've already covered the root locus strategy for an analog system. The rules for constructing that are the same in discrete time. It's just where is stability in the S-plane versus where is stability in the Z-plane. In the S-plane, it's the entire complex left half side of the S-plane. In the Z-plane, where's stability for a causal waveform? The unit circle. You need your poles to closed loop poles inside the unit circle. The drawing of the root locus is the same. It's just you obviously have different regions to worry about for discrete time versus continuous time. And we'll get into that with unit number 6. And I hope I don't have to remind you too much, but our third exam is 2 weeks from today. Wow, the semester is flying by. Here's what I want to do, and this is to orient you relative to those supplemental lectures. This is lecture 5.4 in Unit 5. And today what I want to do is spend some time going over or talking about homework number 5, and then we'll try to provide a little bit of justification behind the Ragazzini restrictions. That kind of has a ring to it, the Ragazzini restrictions. But what is going on, or why do we have those 4 restrictions? And hopefully we will have time to get into PID controllers and what is behind that. What are these 3 different pieces? PID, I'm saying it PID, I'm not saying PID, I'm saying PID because it's proportional, integral, and derivative. And each of those are then operating on the air signal to create an input to your system in the closed loop setting. And that will actually bring us into starting with the P part. So in PID, you could actually have a P controller, you could have a PI controller, you could have a PD controller, or you could have a PID controller. You could have all different kinds of combinations of the PID. We will start with the easiest, the P controller, the proportional, and that will allow us to actually start talking about this strategy of root loci. And all of that is really, what do I want to say other than it's motivated, or the underlying process of the root locus is focusing on the closed loop denominator, which influences stability and performance of your closed loop system. The root locus all hinges on this 1 plus k g bar of z, where g bar of z represents this cascade or series combination of your controller and plant. And that will make more sense as we go through. Homework hints or help. In problems 1 and 2, and if you're following along at home, you might want to pull up homework number 5, that assignment, so that you understand what it is that I'm talking about. So here it may be a little bit odd as far as what in the world is he talking about, but hopefully you can, when you're going through homework number 5, it will start to make more sense what we're talking about now. In homeworks 1 and 2, I'm asking you to create a desired closed loop transfer function, a capital T sub c of z. And I believe in every one of those cases, there's maybe 6 different transfer functions spread out among problems 1 and 2. I think I'm forcing the numerator to have that structure, a gain and a 0 at the origin. You don't have to design that, that's been given. What you do have to design is the denominator, and I'm assuming that that denominator is second order. And how do you find? So what you're trying to determine are these 2 coefficients, an alpha sub 0 and an alpha sub 1, based on satisfying these design specifications or performance specs. And if you want to try to remember what is going on with these performance specs, you have 3 different sources of material. The notes and videos from lecture 5.1, 5.2, and 5.2S1. Those talk about these concepts of performance specifications. As a reminder, if we start talking about settling time, you should be thinking circles. a bullseye. Settling time now means circles. Or settling time is saying, oh, we're dealing with the radius of these complex poles, or the distance these complex poles are away from the origin in the z-plane. And we can find this radius r from this 1% settling time condition, which is the radius raised to the n. When does that, what value of n causes that quantity, r to the n, to be less than 0.01? That's how we're defining the 1% settling time. And you know how to solve that equation for r. Take the log of both sides and then maybe the anti-log, and you'll end up with an expression for r if somebody gives you capital N, or the settling time in units of seconds, for example, t sub s, capital T sub s. If you want your settling time to be shorter, what does that mean? Do you want a slower system or a faster system? This is now a fill in the blank, and I have two answers on that blank. I need you to circle. So I guess slower is up and faster is down. Can that be any more confusing just because slower is above faster? Or do you want to do it the other way around? This way everybody will be confused, and so if you get your thumb in the wrong direction, you can just say, well, it wasn't clear what you wanted. But slower is up, faster is down. If I want a shorter settling time, I want which direction of your thumb to be accomplished. So I want you to say slower is up, faster is down with the count of 3. 1, 2, 3. And if you're unsure, I guess your thumb is parallel, right? But here you want a faster response. If you want a shorter settling time, that means you're making your system faster. So the system is faster with a shorter settling time. And what does that mean relative to the circle around the origin in the z-plane? Is it smaller or larger? Is your circle in the z-plane around the origin, to obtain a shorter settling time, should that circle be smaller or larger? 1, 2, 3. Now most of your thumbs should be, well, your thumb should be up, and I see most of them are up in this case. So we wanted a smaller circle in the z-plane to correspond to a faster system. And here's the picture, or here is a picture for that. R1 and R sub 2. For this to even make sense in a discussion about settling time, what can you tell me about capital R sub 1 as far as its value? Can you say anything? If we're talking about settling time, what can you tell me about capital R sub 1? Its value. Can you say anything about that? If we're talking about settling time, where can R sub 1 not be? It can't be bigger than 1, can it? So R1 and R2 have to be inside the unit circle in order to even have this discussion of settling time. That's the question I was trying to get you to think about. So if we are talking about settling time, we have to have all of our poles inside the unit circle. In this case, R2 is obviously less than R1, and R2 then produces a faster or slower response. So now my terms are interchanged. Faster is up, slower is down for your thumb. R2 produces a blank response versus R sub 1. So relative to R sub 1, R sub 2 produces, show me your thumbs at the count of 3. 1, 2, 3. So now this is giving us a faster response relative to R sub 1. So R2 poles are faster than R1 poles. That's problem 1 and 2, but you're going to have to do more than just settling time. You'll have to do peak time, maybe combined with settling time, peak time and percent overshoot, and settling time. Those combinations of performance specs should inform your decision on where you put your poles. And once you've located your poles, you now have some z delta r e to the j theta sub d, and that now defines where your alpha 0 and alpha 1 are. Problem number 3. Maybe that was problem statement-wise a little vague, but I'm assuming that to control this system, I think problem 3 is asking for a Ragazzini design controller. I'm assuming that you're now trying to control this system, and the system actually was g of s equal to 1 over s minus 1. It's an unstable system. I want you to design a stabilizing controller. And in that sense, I'm assuming a zero-order hold equivalent needs to be determined so that you can start with a capital G of Z. And the zero-order hold equivalent of a G of S is now you just put another pole at the origin in the S-plane, find the Z transform of that G of S over S, which in this case is 1 over the quantity S times S minus 1, and then multiply it by this 1 minus Z to the minus 1. That gives you G of Z. Or if it's late on a Friday night and you're doing this, you could do it in MATLAB. That's fine, as long as you know what you're pursuing. Here's your question.
Yeah. I'm trying to understand, make a connection between what the continuous time transfer function and the zero order hold, how that relates to the real world.
So all of this, so where is this relative to the real world? And here what you have is a G of S, which I've now said is a G of Z for some reason. But if you now had a analog system, we are assuming now that you have this in a sampled form. So in front of that, you would have this zero-order hold. You now are going from a discrete to analog conversion, but here's our zero-order hold, and here is just the opposite. Here is our analog to digital. And what we are then doing is asking to find what's this capital C of Z in this interconnected block diagram. And we'll build that C of Z using Ragazzini's approach. And so what we're doing now is we're finding this G of Z, which combines the zero-order hold and the analog plant to create a capital G of Z. And once we have a capital G of Z, we can go to town. Now we can try to figure out what is this capital C of Z. And to find that G of Z, you could do it, as I just said, by hand. But by hand means find those formulas in the table and just write down the Z transform of that. Or use MATLAB and boom, out comes an answer. So I'm giving you the answer for capital G of Z right now. But in MATLAB, you would simply take this transfer function G and put it through the C to D function with a sample period of 0.1. And out pops your discrete time plant capital G of Z. The default on this C to D function is actually to default to a zero-order hold equivalent. And so you don't have to put another argument, a third argument in that function and put it in quotes and tell it what you want it to be. It will just default to the zero order hold equivalent, which will now give you a capital G of Z. And where's the pole of this G of Z? It's at the value of Z that causes that denominator to vanish. The pole is at 1.105. Where is that relative to the unit circle? It's outside. It's unstable, and we started with an unstable analog plant, didn't we? It was a pole in the right half plane. So now we want to use the Ragazzini approach to try to stabilize this unstable system. And where are your finite zeros for capital G of Z? We don't have any, do we? So what are we going to do with restriction 2? We can jump over it, can't we? Do you remember the exercises we were doing last time? Hopping and skipping? Yes. So the question is, are we going to worry about positive feedback? We only get positive feedback when we're low and we need some help, right? In this class, we want negative feedback. We want negative feedback. Ooh. So you want to be thinking negative feedback, but if somebody gave you a positive feedback, that's just going to change the sign in your feedback path and you can stabilize the system that way. So I wouldn't get too hung up on whether it's positive or negative, but we'll just be using that negative sign in the feedback path. We're done because I can't write anymore. I used my right hand to emphasize negative. I should have used my left hand. But we'll try to continue. In this case, what's the pole zero excess for capital G of Z? That's 1. We have one more pole than 0, finite 0. And what do we know about the pole zero excess of our plant and the pole zero excess of our desired polynomial? And in this problem, we're actually saying make the response deadbeat. And for a deadbeat response, we put all of our desired closed loop poles at the origin. So here I'm giving you a hint, a big hint. Try to use this, T sub C of Z, as your desired closed loop transfer function. And what you're trying to do now is figure out, can I find one unknown, capital K, based on the design specifications? That's problem 3. Trying to find K. Here, boy. Where's K? So you find K, and you're done. But now you've tried to motivate that. Problem 4. I give you a transfer function, a Z domain, a discrete time transfer function, and I want you now to control that based on the Ragazzini design approach. And I believe in this one I also say we've already focused on problems 1 and 2, finding poles. Here, let's just throw that away and say, let's just put them at the origin. Let's have a deadbeat response. Let's not mix all of these different. But in real life, you would want to be mixing all of these. And on the exam, you'll probably have a mix of finding these Z deltas and using those to design a capital C of Z. What's the pole zero excess for capital G of Z? Then our desired, this is really hard, isn't it? Our desired closed loop transfer function, capital T sub C of Z, must have a pole zero excess of at least 1. It can't be 0. We can't have the same number of zeros as we have poles, since our plant has a pole zero excess of 1. G of Z, the original plant that we are trying to control with this Ragazzini controller design strategy, has an unstable blank. Is it a 0 or a pole, or do you have both? The open loop system has an unstable 0 and it has stable poles. So in this case, we have an unstable 0. And what restriction does that now activate or make us have to deal with? And you don't have to know all of these restrictions as far as which one's 1, 2, 3, and 4. You just have to apply 4 of them. But hopefully we'll kind of all be talking the same language, and this is restriction 2. We want a deadbeat response, so all of the poles are at the origin. We may just need to figure out what's the power on that Z. And if we have a pole 0 excess of 1, and restriction 2, what's restriction 2 put into play? If we have an unstable 0 in our plant, what does that force on T sub C of Z? Or does it force something on 1 minus T sub C of Z? Do you remember? So we're not wanting to cancel poles and zeros of our unstable poles and zeros of our plant with our controller, and that forces restriction 2 and restriction 3 into existence. Restriction 2 is dealing with an unstable 0, and I'll just tell you, I'll remind you that that means that we need to place into our desired closed loop transfer function a 0 factor at that same location. So we need to force T sub C of Z to have unstable 0 factors consistent with our unstable 0 factors in the plant. So the third restriction deals with 1 minus T sub C of Z, and that's when we have to worry about unstable poles. And we'll get to that maybe when we talk about these restrictions or where they're coming from. But now we need to really just copy down that 0 factor that's unstable in G of Z, put it into T sub C of Z. So now we have a Z minus 1.1. We're going to need probably a gain, but if this is K times Z minus 1.1 and we want a deadbeat response, and what else do we need? We need T sub C of Z to have a pole 0 excess of at least 1. What do we know that power on Z in the denominator needs to be at least what integer value? Has to be 2 or bigger. That's a 2 if you can see it. So that's Z squared in the denominator, and so this is what I would recommend that you try to achieve. I wouldn't put 3 in there or 4. The question was, we can put whatever. That's really going to make your desired system slower than your starting system G of Z if you make it that much bigger. And it will make your design a little bit more challenging probably, because now you have a cubic to work with when you're trying to solve some of these additional conditions, which might be based on the DC gain of your system. If you now wanted the DC gain of your system, or if you wanted 0 error due to a constant input, what would you want the DC gain to equal of your desired closed loop transfer function? If I put in a 4 as my reference input and I want my output to equal 4, what does that say about my DC gain? It needs to be 1, doesn't it? So now I'm saying that this needs to be 1, and how do I determine the DC gain of my closed loop transfer function? Where do I evaluate this T sub C of Z? At what value of Z? If I'm doing sinusoidal or frequency analysis, I'm on the unit circle. And where is DC on the unit circle? It's right out there at z equal to 1. So I'm evaluating this at z equal to 1. So putting all of these pieces together, here's my desired closed loop transfer function. I know what g of z is. I now need to compute capital C of z to satisfy these design specs, and I'm going to use k then as a design parameter. That's the help for homework number 5. And that should make your life easier in terms of solving those. I hope. That's the intent. Question? Well, I'm not sure what the question was. This, I've already solved it, and I've come up with k being negative. I don't remember the answer, but it might, depending on what your values are. You now have an unstable plant, and you're now trying to stabilize that. But I would just go through and check to make sure you haven't made a sign error in all of your analysis, and in particular when you're plugging in to the controlled design formula, make sure that everything appears okay. But I don't remember the answer. K could be negative. Now what that's implying is that this assumption of negative feedback may have been in error if you wanted to think about it that way, but it's really just saying I'm turning around essentially based on having negative feedback. So your gain could be many different values, but typically it's positive with negative feedback. But it might turn out to be negative. Let's now talk about these Ragazzini restrictions. We have 4 of them. And most of them are based on this design formula. And this looks a little bit messy, but hopefully it's somewhat helpful. Creating this controller transfer function, capital C of z, is done by taking 1 over g of z. 1 over g of z, what's that doing? That's really inverting the plant. That's like saying, oh, if the plant was 5, I could multiply that by 1 over 5, and now I would have basically a clean 1 gain between the input and the output. And then I can sort of say, oh, what do I need to do to achieve my closed loop behavior? I now need to scale that by t sub c over 1 minus t sub c. And that would give me my desired closed loop transfer function. In this expression, if your plant, and now I'm circling g of z, if your plant in fact had unstable zeros, those would actually end up in the denominator of your controller because they're in the numerator of your plant and you're putting the entire plant in the denominator. So the numerator of your plant now becomes your denominator of your controller. Is that making sense? So think of g of z as a rational transform, and you have zero factors and pole factors. The zero factors, which I've highlighted in red or hashed in red, and the denominator factors I've hashed in blue, those actually will pop upstairs because they're in the denominator of the denominator. But let's focus on the red first. If I don't want my C of Z, if I don't want my controller to be canceling poles or zeros outside the unit circle, then I can't have unstable poles equal to the unstable zeros of my plant. And to avoid that, to make that not appear, I need to put those same factors in the numerator of t sub c of z, my desired transfer function. If I have those same factors, then they will cancel each other and they won't appear in capital C of z. I'm not saying that you can't have an unstable controller or unstable zeros in your controller. I'm saying you can't cancel unstable poles and zeros with your controller. That's kind of a subtle distinction, but you need to be clear on what I'm trying to say in that sense. So if you had an unstable zero factor in g of z, and I would just play around with this and just see if it makes sense. Let's say that I now had a unstable zero in my plant at z equal to 1.1. So that corresponds to having a factor of z minus 1.1 in the numerator of g of z. Well, I now cannot have that in my denominator of my controller, c of z, and a way to avoid that is to put that same factor in the numerator of t sub c of z. If it's in the numerator of t sub c of z, that factor is going to cancel that numerator factor in the denominator of g of z. I would just plug in some expressions and make sure it's clear in your head. We don't want c of z, capital C of z, to end up canceling poles and zeros in the closed loop system. This is in the design process. We can cancel those in the design process. This is the process that I'm using to create my controller. So I can kind of understand your confusion. I thought you just said not to cancel, and here you're canceling. Well, that's exactly what I said. But here we're doing it on the controller. We don't want our controller to eventually cancel unstable poles and zeros in g of z. In the design process, that's exactly what we want to do, so that they don't end up canceling when we plug them into, or when we have our controller capital C of z. It's a little bit subtle or confusing, but you need it to be clear before the exam, obviously. Similarly, if you had unstable poles in g of z that I've highlighted or hashed in blue, you need now zero factors in the 1 minus t sub c of z to cancel those. So you are going to create t sub c of z with some unknown variables, so that when you evaluate t sub c of z at these unstable pole locations, 1 minus t sub c of z will vanish, so that that zero cancels the zero factor, or the pole factors in g of z.
So we're multiplying c of z times g of z again after we.
So in the real world, or when we implement this controller, this is what we are going to be doing with our controlled system. We will have a c of z multiplying g of z in the closed loop. That's where the controller is multiplying the plant. That's where we do not want cancellations to occur that are unstable. We can't have c of z canceling unstable zeros or poles in g of z. That's where we multiply g times c, or the controller times the plant. Is that clear? And we're trying to avoid that in the design process in this design formula, this controller design formula. We want those cancellations to occur here so that capital C of Z, our controller, won't be stepping on or trying to cancel those unstable poles and zeros in G of Z when we start to implement this controller. Have I confused you completely? If I have, go home and start playing with unstable poles and zeros. And just play with one at a time and see if it starts to make sense as far as why are we messing with 1 minus t sub c, or why are we messing with the numerator of t sub c.
So like the term with the t sub c, and it kind of looks like a feedback.
So no, so here don't worry too much about t sub c, or what it looks like in this expression. We're going to derive this formula. Don't worry about what it looks like here. T sub c of z is what? Just keep that in mind. What is T sub c of z? That's a transfer function, but it's the desired closed loop transfer. That's what we want the closed loop system to look like when we're done. And it just so happens that this formula makes that true, or achieves that. Now, that's restriction 2 and restriction 3. We have the others that bookend those restrictions, restriction 1 and restriction 4. This restriction 1 is a little wordy, but you can read it on your own. You don't have to copy it down, but later you can try to figure out what in the world was he talking about. The background behind restriction 1, it's all based on keeping what? Capital C of Z, your controller, causal. And are we clear what that means? If your controller is not causal, that would mean that somehow it can predict the future. It can start moving before you even give it any information. That's not going to happen, is it? So we need C of Z to be causal. That's the whole point behind restriction 1. Just keep that in mind. Restriction 1 says the controller needs to be causal. And the way to guarantee that is to make sure that your desired closed loop transfer function, T sub C of Z, has at least the same pole zero excess as your original plant. You can't make the delays between input and output in your desired closed loop system less than what you started with. You sort of can't create the impossible. And that's what I'm trying to say with these explanations. The pole zero excess in G of Z will result in poles at infinity in C of Z. Poles at infinity, that just means that you have, when you let Z go to infinity in C of Z, it would go unbounded. That means the numerator of C of Z is bigger than the denominator in order. That's poles at infinity in C of Z. The pole zero excess in G of Z will result in poles at infinity in C of Z unless the desired closed loop transfer function, T sub C of Z, possesses at least the same pole zero excess as G of Z. If you want to impress your roommates or buddies or friends, you just start quoting this sentence, right? And they're going to be going, just go in the other room, talk to yourself. But you need to understand what this is saying. And what is it saying? It's basically saying poles at infinity in C of Z would cause C of Z to be non-causal. And we can't have that. Another way of looking at that is to say that this restriction on the pole zero excess in the desired closed loop transfer function, T sub C of Z, makes sense. Meaning, suppose G of Z, the original system, had a pole zero excess of 1. What can you just think about in terms of a plant that has a pole zero excess of 1 and it's a simple plant? 1 over Z, a unit delay, right? So now if you had a plant that was as simple as just a unit delay, so you have an input, you hold on to it, and then you just hand it over after 1 delay. That's a pretty simple plant. If you had a G of Z that had a pole zero excess of 1, then G of Z would have to have a 1 sample period delay between the input and the output, forcing your desired closed loop transfer function to have a pole zero excess of 1 means we're forcing that desired closed loop transfer function to have at least the same amount of delay as the original plant. So if the plant has a delay of 1, you can't have a desired closed loop transfer function that doesn't have a delay. That you give it an input and it immediately comes at the output. That's what we're meaning by this. Maintaining at least the pole zero excess in the desired as in the original plant. That's restriction 1. Let's derive this controller transfer function, or this controller design formula. Where is this coming from? This will just be a little block diagram algebra, just some algebra with transfer functions. And now we'll try to slow down and make that happen, or derive that. So here, let's find this controller, C of Z. What does that need to equal so that the closed loop transfer function between the input R and the output Y ends up being capital T sub C of Z? That's where this formula comes from. And this structure is fixed. We have unity feedback in the, or we have a gain of 1 in the feedback path. We don't have any transfer function down here. That's 1. We're measuring the output and then negating it and comparing it with the reference, and that gives us an error signal. And that error signal then drives the controller's output, which we could call a input to the plant. Now achieves some, after some dynamics, whatever is in the plant, an output response. And then whatever is coming at the output, we feed that back and compare it with our reference input. Ideally, we would want the output Y to be tracking the input R. Or when we compare these two, R minus Y, E, we would like to drive to 0, usually. Or we want to make it very small. We want the error between where we want to go and where we're at, maybe we want that to be very tiny, typically. That's the block diagram. That's what we're saying, and that's why this minus sign, that's where the negative feedback comes from, is usually we're comparing one signal with the output. And that produces an error, a difference. If that's the case, let's use that to try to derive what C of Z equals. Y of Z, you should be able to see just from this block diagram that that's G of Z times C of Z times E of Z. And typically when you're doing this block diagram algebra, you probably want to be writing some of your equations in terms of outputs of the summing junctions. And what's the output of this summing junction? It's the error signal. Let's write that equation. E of Z is in fact just R of Z minus Y of Z. I think I'm going to get sloppy and drop the arguments, the Z's. But now we have a way to replace E in the first equation with R minus Y, and we'll have one equation containing only R's and Y's, and that will allow us to find a transfer function between the two. Or now we have Y of Z is equal to GC, I told you I was going to get lazy, times R minus Y, where this is just E. That's really just rewriting the first equation. Now let's combine the terms that involve Y and the terms that involve R. Or let's add to both sides of this equation GCY. If I add GCY to the left, I have Y plus GCY. Let me factor out that Y, and I have 1 plus GCY. And that's equal to, on the right, the only thing that's left is GCR. And this actually gives us our desired closed-loop transfer function. We now know that y of z, if we now solve for y of z, is g of z, c of z, over what scaled y of z before, which is 1 plus g of z, c of z, and all of that is scaled by the reference input signal R of z. Or if we wanted now to describe this, that's actually our desired closed-loop transfer function. That's the transfer function between our reference input R and the output Y. If T sub C of Z is equal to G of Z, C of Z over 1 plus G of Z, C of Z, then we need to now solve this for C of Z. Now, to go back a step, this transfer function, T sub C of Z, assumed the block diagram that we started with. That block diagram had that negative sign. And that negative sign was really right there, which was right here, and that translates over there to that plus sign, so that negative feedback gives us a denominator of 1 plus G sub C, G of Z, C of Z. If you had positive feedback, the only change that would occur in this transfer function would be 1 minus G of Z, C of Z. So that would then give rise to maybe a negative sign on your gain. If you forgot and you said, oh, I'm going to have positive feedback, then if you did the analysis, you might end up with your gain being opposite to what somebody else might have had if they had negative feedback. They will take care of themselves. Question? So the question was, what if I have something in the yellow circle, let's say an h of z? You could derive these formulas with that h of z, just include it in your analysis. It's fine. It's just, let's make this a little bit cleaner and just leave that as unity. Here, capital H of z is equal to 1 in our feedback path. Now what are we doing? Well, in this Ragazzini design approach, we start with our plant, G of Z, and we say, let's figure out what we want T sub C of Z to be. And we specify what it is. So now we have T sub C of Z, and we have G of Z. What we don't know is C of Z. So let's just solve it from this relationship. That's all we're doing, and that's how we find that controller design formula. Let's now sort of back that out. In this case, we are given T sub C of Z based on design specifications or performance specs. We know our plant G of Z. What we don't know is C of Z. Let's solve for it. If we cross multiply in this t sub c expression, then we have 1 plus gc times t sub c is equal to gc. I've just cross-multiplied or cleared the denominator in that expression for t sub c of z. Let me distribute t sub c, and I'm assuming right now, because of the way I'm manipulating this, that I have scalar transfer functions. C is just a numerator over denominator. I don't have any matrices floating around in here. Everything are scalar transfer functions. That allows me to slide these transfer functions around arbitrarily, really. And now what do I want to do? I'm trying to now solve this equation for C. So let me put C terms on one side and the other terms on another. Or I now have t sub c equal to gc minus gc t sub c. Or this is now, let me factor out a g from the left. Let me factor out a c from the right. I feel like I'm cheering here. Give me a g, give me a c. What's in the middle? Is that clear? That if I multiplied that right-hand side out, I would have gc minus gc t sub c. And since these are scalars, I can commute c and t sub c. That's how that magic occurred. It really wasn't any magic. And do you see now how to solve for c? So now I really just have t sub c is equal to g 1 minus t sub c times c, and I can divide all the terms that are scaling c to isolate c, and that's my controller that I'm trying to solve for. Therefore, capital C of z is 1 over g of z. I just divided both sides by g sub c, and I'm dividing both sides by 1 minus t sub c to have t sub c of z over 1 minus t sub c of z, and this is my direct controller design formula. We've talked about restriction 1. That forces the pole zero excess to be the same between our plant and our desired closed loop transfer function. We've talked about restriction 2 and restriction 3. Those are trying to make sure we don't cancel unstable zeros and unstable pole factors. Now we need to look at restriction 4. And restriction 4 is dealing with steady state behavior or steady state accuracy. Or if I put in a constant, what's the output? The difference would be my error signal. That's my steady state accuracy after the transients have all disappeared. And how long does it take for the transients to disappear? 5 time constants in continuous time. Here it's so many sample periods, isn't it? And that's our definition of infinity, really. So now, when is infinity a small value? In this controls class, you could go an infinity in time by taking r to the n equal to 0.01. We're 1% settling time. And that may be the trade-off, is transient behavior. How quick is that happening relative to how much error is happening in the steady state. Steady state accuracy constraint is what I would maybe classify restriction 4 as. Or restriction 4 may say that the steady state accuracy may impose additional constraints on our desired closed loop transfer function as z goes to 1. Let's just see if we can get a feel for that by an example. In the block diagram that we have assumed, and what we've assumed is h of z, the feedback path is unity, h of z is 1, what's e of z? How do we define the z transform of the air, e of z? What was that equal to in this block diagram? It's just r minus y. But what is y of z in terms of r of z? What's the output in terms of the input? It's the desired closed loop transfer function times r of z. This is simply y of z. Or we now have a formula for the air. E of z is now 1 minus t sub c of z times the reference input. So if somebody said, oh, can you tell me or give me a formula, a time domain expression for the air relative to a reference input, all you would need to do is inverse z transform this expression. 1 minus t sub c of z times r of z. If we want 0 air, E of z going to 0, if we want 0 air due to, let's say, a constant reference input, which I'm just going to say input, if r of z is a constant, if little r of n is a constant in the time domain, let's say it's a constant of a, then its z transform would be az over z minus 1. And if we now apply the final value theorem, will allow us to solve for this air in the time domain. The infinite horizon air in the time domain, little e sub infinity, is equal to the limit as n goes to infinity of little e of n. That's in the time domain. And now we can invoke the final value theorem. The FVT, the final value theorem, says that that's equal to the limit as z goes to 1 of z minus 1 e of z. That's the final value theorem, those two sides of that right-hand equality sign. let's now plug in the structure that we know exists for capital E of z. This is now equal to the limit as z goes to 1 of z minus 1 and E of z, well, that was 1 minus t sub c of z times r of z, which was a z over z minus 1. And before we make z march off to 1 or go to 1, let's cancel the z minus 1 factors so that we don't have 0 over 0. Let's now cancel those. And if we want the error to go to 0, we want this to equal 0. What do we need to have happen if we want that formula to equal 0? Do you see that we want the limit as z goes to 1 of the quantity 1 minus t sub c of z to be 0? Because a is a non-zero value. We could divide that out if we wanted. Z going to 1 in the right-hand side parenthesis is just 1 times a. And to make that 0, we have to force 1 minus t sub c of z as z goes to 1 to equal 0. Or we could say then that the limit as z goes to 1 of t sub c of z must equal 1. And it's all playing on that. We're forcing that to equal 1 when we take the limit as z goes to 1. But what is happening to t sub c of z when z goes to 1? What have we called that? Or we could say that the t sub c of z at z equal to 1 is equal to 1. We're just calculating the DC gain of that desired closed loop transfer function. We want the DC gain of the closed loop transfer function to be equal to 1. And then if we put in a 5, we get a 5 out. Because t sub c in steady state is 1. So whatever we put in for r, it's going to be equal to y, or y is going to equal r, if we have this condition. If it happens that we are not commanding something to be constant, but we want it to actually ramp up with time, and we want to maybe be close to that value. Let's say that we're building an oven, which we tried to do. We tried to build an oven and put it on Mars so that we could do some analysis of heating up this oven and see how exothermal and endothermic reactions were, where they were occurring, so that we with temperature, and then we could determine what kind of material we had in that oven on Mars. So we were trying to ramp up the oven temperature, and we wanted to track that. Or we were basically saying, here's our command for the oven. We want the oven to actually track that temperature. So we wanted it to be close. We want a small velocity gain constant. That's what it says. Well, then this gets a little bit different in terms of the formula. But now we would have minus t d t sub c of z dz equaling 1 over k sub v. The velocity air constant, if we make that really big, then the air is going to be small. And we would want this to also be true when we already have, if I put in a constant value, I would track that constant without any air. When t sub c of z at z equal to 1 is equal to 1. What's the subscript on k? That's a v. So it's the velocity gain constant, k sub v. And this is assuming that we already have set the DC gain to 1. So if somebody said, oh, I want to make this even more fancy, I want to track a ramp with a certain amount of air, then you might have to put in some more unknown parameters in T sub C of Z, make it a little bigger in terms of unknown parameters, increase your polynomials in the numerator and denominator potentially to give you some more flexibility to achieve these design specifications. And that may be talked about in a subsequent video, lecture 5.5. Ragazzini design number 2, example number 2. Questions on Ragazzini? Let's talk then about PID. PID. No, don't say PID. If you're in an interview and somebody writes PID controller on a piece of paper and said, can you tell me about this controller? Don't say, you mean a PID? Don't say that. Say PID, and at least you'll get that far through the interview. Then you'll say, oh gosh, what's P, what's I, what's D? It stands for something. Well, it stands for proportional, integral, and derivative. And what I want you to try to get from this last couple of minutes is this concept. The air signal, remember, we're trying to maybe drive that air to 0. And each of these 3 component parts of an overall PID controller influences how you manipulate or adjust your control signal U based on the air E. The proportional will be direct in time, and maybe I should just let me slide on down here. Here's the picture you might be thinking of. Proportional is working on the air right now. The integral, you're integrating from some previous amount of time up to the present in your integral controller, so you're working with past airs in your integral piece. The derivative piece, that's trying to anticipate where am I going. If you're now taking the derivative of the air, and the air you're saying, oh, it's going up, now you can make a correction based on what you're anticipating, or the future behavior of that air is based on the derivative. This PID controller then has 3 different pieces to it. One that's sort of playing with the air now. The integral is sort of saying, oh, I remember where you were at before, and working with that. And the derivative is saying, oh, this is where we're going, then I'm going to adjust my behavior in a certain way. That taken into account, or another way to think about that would be the integrator is worrying about steady state accuracy. If you want to try to improve your steady state accuracy, you might want to involve an integrator or introduce an integrator. If you're trying to speed up your system behavior, you may want some derivative action, the D. Question? So now the question was, how would you maybe realize these in an analog circuit? You could build each of these pieces with an op-amp. You know how to build a gain with an op-amp, a couple of resistors around that op-amp. An integrator might be a capacitor and a resistor, and a derivative would be switching places with that capacitor and resistor. That would be a way to realize these in an analog control setting. We're going to figure out how to do this with a difference equation. eventually. But we'll have then a proportional piece, an integral piece, and a derivative piece, or correct, a PID controller. So we'll pick up at that point on Monday.